Moment of inertia, also known as rotational inertia, is how easy or hard it is for things to spin. Physics operates in much the same way whether you're moving in a straight line or whether you're rotating in a circle. In straight line motion, we had acceleration, changing your motion, speeding up, slowing down, or turning. It was caused by a net force divided by your mass. Things moved and kept moving because of conservation of energy. They had kinetic energy, 1/2 of your mass times your velocity squared. Each one of these quantities has a direct analogy in rotation. Your angular acceleration is caused by a net torque, that twist, that force applied to cause rotation. What slows it down? Not mass, how hard it is to move, but rotational inertia, how hard it is to rotate, to spin, to twist, to turn, or topple. Kinetic energy works the same way. Rotational kinetic energy, the energy you need to turn in a circle, is 1/2 times how hard it is to rotate times how fast you're spinning squared, just like it was 1/2 times how hard it was to move times how quickly you're moving squared. Let's first get a sense of how rotational inertia works. Low inertia means it's easy to move, and low rotational inertia means it's easy to spin. Take a look at this denominator. If you have a very low denominator with a small number, you're going to get a big angular acceleration. You will speed up quickly. You will stop, slow down quickly, and you will turn, change direction, or in this case, fall over quickly. A small denominator means that you can have very, very large changes. It will be very easy to start spinning, and it will be easy to stop spinning. High inertia is therefore much harder to spin. Again, look at the denominator. If you have a very large rotational inertia, very large denominator, you're going to get a small angular acceleration. You may have a huge torque twisting you around, but you won't speed up very quickly. You won't fall over very quickly. You won't change direction or slow down or stop very quickly. High rotational inertia means it is hard to start spinning, but it also means that it's hard to stop spinning. Athletes and animals have this down to a science. Think of divers, dancers, figure skaters, anybody who wants to turn very, very fast. Check it out. What does the dancer do with her arms as she goes into the turn? Look at the way she changes her body when she wants to start spinning. Look at the changes she makes when she wants to stop spinning. Look at the diver. See the way he turns and pulls his body in when he wants to start spinning, and the way he straightens out when he wants to stop spinning. Several people said this in class already. If you want to start spinning, speed up, spin faster, get into the right position very quickly, you pull everything you have in. When you're ready to stop spinning, when you want to land, you stretch everything out. Watch that sequence again. Watch the way the dancer starts to speed up and then slows down. Higher acceleration, spinning a lot slower. Now, try this on your desk at home. Take something with movable mass, compact it in very, very close to the center, give it a twist. See if you can twist it really, really quickly, like 10 times in 5 seconds. Then move the mass out again as far apart as you can. Spread everything that can be spread. Again, try to twist it 10 times in 5 seconds. See how quickly you can twist. Pull your siblings in. See if you can race. You can find the full set of instructions for this demo with a meter stick and 2 cans on YouTube. It looks like this. Try it with water bottles or anything you have. Which sister is having an easier time twisting, turning, spinning faster, and which one is really going to have to work on it? Conclusion. Low inertia, that is to say, it's easy to spin, to start spinning, to keep spinning, to stop spinning, is mass that is compact, that is near the center. It is close to the axis of rotation. You'll have a much harder time with the high inertia, objects that are hard to spin, hard to stop spinning, hard to keep spinning, hard to start spinning, if your mass is way spread far away as possible from the center or the axis of rotation, open, airy, hollow. Check out, most of the mass of this wheel is out here on the metal rim. Here towards the middle, there's hardly anything at all. Contrast that with this wheel that had all of its mass packed very closely in. For your first year of physics at least, the math for rotational inertia is going to be look up the formula on page 128 of the Hewitt or 256 to 258 of the Holt. But we can't just leave it like that. The math has to come from somewhere. Rotational inertia starts with the idea of rotational kinetic energy. This wheel is traveling round and round and round. Well, all right, it's not traveling round and round. It's staying right where it is. But if you look at the individual bits on the wheel, if you look right here where you'd pump up the tire, you'll see that that position, that point, is actually moving. It's got kinetic energy. Every point on the wheel, look at all those little rectangles around the rim of the tire. Every single one of those is moving. If you add up all the kinetic energies of all the little rectangles, all the little trapezoids, all the little circles that make this wheel, you'll get the rotational kinetic energy that keeps them all moving round and round in circles. Now, add up all those 1/2 mv squareds. You'll notice they're all traveling at different rates. This is what we said in class and what you read in your book about angular speed versus linear speed. This rectangle out here has to make this huge big circle in the same 1 second that it takes this little circle here to make a much smaller circle. The ones on the outer lanes are technically traveling faster. You know this. It's why you want to run in the inner lane when you're running the mile in gym class. What is the same for all of them is their angular speed, the number of laps per second, or rotations per minute that they go round and round. In your car, you call this RPM. So while they have different V's, their omega, their angular speed, is the same. The formula that converts from V to omega has a conversion factor of R, meters per radian. Let's substitute this in for V. They're all going round and round at the same rate. What's different is that these little circles have a small radial distance, r, and these big rectangles have a big radial distance, r. Well, if this is constant, we can pull that out, and 1/2 isn't going anywhere, so we can pull that out. So what are we going to get for rotational kinetic energy? We're going to get 1/2 times some junk in the middle times your rotational speed, your angular speed squared. What's the junk in the middle? Well, I don't like the look of this. This looks like nasty. This looks like calculus. But whatever it is, it's going to be something on the form mr squared. How much of this do we have to know for the test? Absolutely nothing. But now it'll make sense when you see a whole bunch of different formulas for I, and all of them are some fraction times mr squared. The mathematics for moment of inertia involve using calculus to add up this piece that's over here, and this piece that's over here, and this piece that's closer in, and this piece that's kind of medium, and this piece this is way far out, to get a whole big picture of the giant shape. Let's start with the easiest shape there is, a circular ring. How much of this metal is out here at a radius from R, from the center? 100%. It's a circle. How much of the mass m is over here at r squared? All of it. Great. There we go then. Your thin hoop, or ring, has a moment of inertia, a rotational inertia formula of I equals mr squared. What if instead of having a hollow ring, you had a cylinder that was all filled in? We'll kind of have to take it for granted that this can is full of can and not, say, tuna fish. Let's just pretend it's a whole solid cylinder all the way through. About how much of the mass would you say has to be moved from the outside to the inside to make this completely solid all the way through? Just guesstimate. Just say a fraction. Shout it out. If you said about 1/2, you're right. The calculus bears you out. The moment of inertia of a full cylinder is 1/2 the moment of inertia that it would have been if all the metal was concentrated around the edges. That means it's 1/2 as easy to spin. What would make this even easier to spin? Well, if we could compact this down to the point that we could shave off some of these inconvenient corners, we wouldn't have these little right angles at the corners and everything would be closer to the center. What shape doesn't have any corners? A sphere. This is significantly easier to spin in your hands or anywhere else and around a nice axis through its center than this. This is 0.5 mr squared. This is 0.4 mr squared. Notice as the shape gets more compact, as we move mass from the edges towards the middle, we go from 100% of mr squared to 50% to 40%. The moment of inertia is going down because the shape is easier to rotate. What if instead of looking at 3D shapes, we look at 1D shapes? Where would you hold this in order to best give it a twirl? You could hold it around one end, when you'd have a moment of inertia of 1/3 ml squared. It would be kind of awkward, though. If you want to twirl this idly, probably you're going to want to twirl it around its center. Take a pen or a pencil off your desk and confirm. This is a lot easier to twirl around than this. If anything, this is harder to twirl. It's much easier to balance. How much easier? 4 times as much. Calculus takes us from 1/3 ml squared all the way down to 1/12 ml squared. All these formulas can be looked up anywhere on the web and in the pages of your textbook. You are not expected to memorize them. Nobody does. You derive them when you need them. How do you derive them? Calculus! You add up this infinitely small piece of mass and this infinitely small piece of mass and this infinitely small piece of mass. It's only about 1/3 or 1/2 of a page of calculus once you count them all up, and you can do any shape in geometry. We're not going to be so concerned about the calculus this year as about the big picture. Consider the shape race from class. Earlier in first semester, we said if they all start with the same gravitational potential energy, they should all end with the same kinetic energy. That means they should be going at the same speed and they should arrive at the same time. But when we try this in class, we find that sliding and rolling have completely different mechanisms. Sliding, everybody arrives at the same time. But if you're rolling, there are winners who arrive first and losers who arrive last. Check out these shapes. Which ones are the ones that are going to get there first? Look for compact shapes versus hollow shapes. Which has low rotational inertia? Which has high rotational inertia? Now consider their angular acceleration. Who is going to accelerate more quickly with a small denominator, and who's going to accelerate more slowly with a large denominator? Now let's think about conservation of energy. Before we knew about rotational kinetic energy, we said that 100% of our gravitational energy went straight into kinetic energy. Now look and see who wins. What if, instead of having 100% of our potential energy be converted to kinetic energy, some of it had to be saved? What if some of it had to be reserved for rotational kinetic energy to roll with? How would that change the kinetic energy that you had left? What if your rotational kinetic energy was even bigger than your kinetic energy? Would that give you more speed or less speed? What kind of value for rotational inertia would give you a bigger rotational kinetic energy according to our formula 1/2 I omega squared? A big one or a small one? Who spins faster? Who travels faster? Consider the shape race, and if you can figure out why certain shapes always are left behind and certain ones always get to the finish line first, you are in good shape.